All right, let's talk about a word that can sound, well, a little scary: calculus. But stick with me, because we're going to blow the dust off of it by solving a really simple mystery that, on the surface, seems totally impossible to solve.
So, here's the big question. How fast is something moving at one single frozen moment in time? We all learned that speed is just distance divided by time, right? But what's the amount of time in an instant? Well, it's 0. And as you probably know, trying to divide by 0 in math just breaks everything. So how can anything even have a speed at a specific instant?
To figure this out, let's play detective for a minute. Here's our case file. We've got an object, and it's been dropped from a super tall cliff. Thanks to physics, we have a formula for its position. S equals 4.9 times t squared. Here, S is the distance it's fallen, and t is the time in seconds. Now, the cool thing is, this formula gives us a ton of data. We can make a table, just like this one, that tells us exactly where the object is at any moment. So calculating its average speed is easy. We can figure out its average speed between 1 second and 3 seconds, no problem. But that still doesn't tell us its exact speed at the precise moment the clock hits 2 seconds.
Okay, to really wrap our heads around this, let's think about it a different way. Picture yourself as a detective. You've been called to a crash scene, and your job is to figure out the exact speed of a car at the very moment of impact.
But of course, there's a catch. You go to check the security tapes, and what do you find? The one camera that was aimed at the exact spot, at the exact millisecond of the crash, it's broken. There's a gap in your evidence. This is our dividing by 0 problem in real life. We can't directly measure the speed at that single instant.
So what do? I mean, you're the detective here. You can't just throw your hands up and go home. How are you going to figure out that car's speed when your most important piece of evidence is missing?
Well, the solution is actually pretty clever and pretty simple. You look at the footage from the cameras just before the crash site and the footage from the cameras just after. By seeing how fast the car was going as it got closer and closer to the crash, you can get an incredibly accurate idea of its speed at the moment of impact.
And you know what? This whole detective method, it actually has a formal name in mathematics. Looking at the before footage is what we call the left-hand limit. We're creeping up on our moment in time from the left side, from numbers that are just a little bit smaller. And the after footage, you guessed it, that's the right-hand limit, coming at it from the other side.
Okay, let's put our theory to the test with our falling object. Here's the evidence from just before the 2-second mark. We're calculating the average speed over shorter and shorter time frames, all leading up to 2 seconds. Now look closely at the data. As that time gap gets tinier and tinier, do you see how the average speed seems to be honing in on a very specific number?
All right, that was the before footage. What about the after? Let's look at the evidence from just after 2 seconds. We're doing the same thing, but our time intervals start right after our target time. And look at that. The speeds are once again closing in on that exact same number, just from the other direction. This is the key right here. The evidence from before the event and the evidence from after the event are both pointing their fingers at the exact same suspect. The average speeds are all squeezing in, converging on one single value, roughly 19.6 meters per second. And that, my friends, is what we call a limit.
Now, this is an amazing estimate, but in detective work and in math, close enough doesn't cut it, right? You need proof. You need the smoking gun that gives you the precise, undeniable answer, not just a really, really good guess.
Let's actually see what's happening. Think of it this way. Calculating an average speed is like drawing a straight line between two different points on the graph of our object's fall. But as we make the time between those points smaller and smaller, as our detective looks at cameras closer and closer to the crash, that line starts to pivot until it's just barely kissing the curve at one single point. That final, perfectly balanced line, that is our smoking gun. It's called the tangent line, and its slope isn't just an estimate. It is the exact instantaneous speed at that one point. The mathematical tool we use to find the slope of that line, that's the derivative. And just like that, the case is closed. The derivative is this absolutely brilliant invention that lets us solve that impossible problem. It gives us the power to measure the rate of change not over a few seconds or even a millisecond, but at a single perfect instant. Okay, so that's a cool little math puzzle we solved for a falling rock. But so what? Why is this idea considered one of the biggest game changers in history? Why does solving this one little mystery matter so much?
It matters because our entire world is in a state of constant change, and the derivative is the language we use to describe that change with pinpoint precision. It's literally how we figure out the exact thrust a rocket needs at the moment of liftoff. It's what powers the models that track the split-second changes in the financial markets. From physics to biology to managing a city's water supply, understanding the rate of change right now is everything.
There's this great quote from the philosopher Alfred North Whitehead that just nails it. He said, "With the calculus as a key, mathematics can be successfully applied to the explanation of the course of nature. It's not just about crunching numbers, it's about describing reality itself."
So, I'll leave you with this thought. We started with a question that seemed to have no answer: how to measure speed in an instant. But now that we have the key, now that we have calculus, what other impossible questions about our universe are just waiting for us to solve?